Hidden behind dense clouds of cosmic dust and a veil of countless stars, right at the very heart of our Milky Way, lies a massive entity that remains invisible to the naked eye, possessing a mass equivalent to millions of suns. This enigmatic celestial object is known as Sagittarius A star. Over the next 80 minutes, we will explore its mysteries. Unlike the violent monsters that power distant quasars and active galaxies, Sagittarius A star remains relatively quiet, yet this silence is deeply deceptive. Beneath its calm exterior lurk powerful magnetic fields, intense stellar winds, and extreme gravitational forces that push the very laws of physics to their absolute breaking point. This is a story of how we discovered the unseen, how we managed to photograph the invisible, and what this supermassive black hole teaches us about the universe and the galactic bulge that concealed the truth for so long. For a vast period of human history, even as we began building telescopes and using scientific instruments to study the heavens, the center of our galaxy remained hidden. Astronomers could map portions of the sky, track the planets, and plot the movements of stars, but something always stood in the way. Whenever they pointed their instruments toward the constellation of Sagittarius, they hit a wall composed of light and shadow, gas, and dust, where stars were packed so tightly that they blurred into a single, indistinguishable mass. This region, which we now call the galactic bulge, is one of the most crowded places in the entire Milky Way. It is a massive central swelling made of hundreds of billions of stars. From Earth, it sits at the heart of our galaxy, but peering through it was almost impossible for centuries. When people look at the Milky Way with the naked eye, they see a faint, glowing band stretching across the night sky, looking much like a thin cloud. But that is not a cloud, it is an incredible density of stars whose light blends into a soft glow. This glow is brightest near the galactic center, but beyond the brightness, there is something else: darkness. This darkness is not an absence of stars, but rather the presence of dust. Throughout the galaxy, clouds of interstellar dust drift between the stars. These clouds are made of tiny grains of carbon, ice, and rock remnants of ancient stars drifting through the void. Despite their microscopic size, they are distributed across such vast scales that they can effectively block light, particularly visible light, which is the kind of light our eyes and early telescopes perceive. This was the fundamental challenge. For most of human history, telescopes only operated in the visible spectrum, acting like giant eyes to collect and focus starlight. However, visible light is easily scattered or absorbed by dust. Because the direction toward the galactic center contains more dust than anywhere else in the sky, astronomers saw only a chaotic mess of dark lanes cutting through thick clusters of stars. The nearby stars were visible, but beyond them lay only darkness. The light from the true center of the galaxy simply could not reach us, as if a heavy curtain had been drawn across the middle of the Milky Way. To make matters worse, the galactic bulge itself added to the confusion. Unlike the flat disk of stars that spreads out like a pancake, the bulge is thick and spherical. Stars in the bulge are packed so densely that their light becomes trapped in a fog of interstellar material. This made our galactic center one of the most mysterious places in the sky. People could see the outer walls of the galaxy and map the nearby stars, but they could not see what was hidden in its heart. They didn't even know if there was a true center, or if the galaxy simply revolved around a loose collection of stars with no fixed point. Some early astronomers even believed the Sun was near the center because they saw stars in every direction, but that was an illusion caused by the dust blocking the real view. In the 18th and 19th centuries, astronomers like William Herschel tried to map the galaxy by simply counting stars in various directions. Without knowing about interstellar dust, they assumed the galaxy was irregular when, in fact, the dust was simply hiding the key evidence. The situation only began to change in the 20th century with the development of new types of telescopes that could see beyond visible light. Scientists realized that to see through the dust, they had to use wavelengths that could penetrate it, such as infrared and radio waves. These forms of light are invisible to our eyes but carry vital information and are not easily scattered. With infrared telescopes, astronomers could finally peek into the bulge and see the stars hidden behind the clouds, allowing them to map the true shape of the center. With radio telescopes, they picked up signals from deep within the galaxy, waves of energy emitted by strange so. In the early 1930s, a young engineer named Karl Jansky was working at Bell Labs in New Jersey. His task was unrelated to astronomy. He was solving problems for long-distance radio communication. He noticed a persistent background noise that could not be explained by static or thunderstorms. Using a large, rotating antenna nicknamed the merry-go-round, he discovered that this noise repeated every 24 hours, or more precisely, every 23 hours and 56 minutes, matching the rotation of the Earth relative to the stars rather than the Sun. The signal was coming from space, pointing directly toward the center of the Milky Way. This was the first time humans had detected radio waves from outside our solar system. Although Jansky's discovery launched the field of radio astronomy, it didn't cause an immediate sensation in the scientific community, which was still focused on optical observations. However, a few years later, Grote Reber, an amateur astronomer, built a 9-meter parabolic dish in his backyard and confirmed Jansky's findings, creating the first radio maps of the sky. By the 1960s and 70s, radio telescopes had become powerful enough to identify a very specific, compact radio source at the galactic heart. This signal, eventually named Sagittarius A star, was incredibly strong and stable, suggesting it came from a very small but high-energy object. To understand its nature, astronomers had to observe the movement of stars around this invisible point. This required extreme precision because the galactic center is 26,000 light-years away. It wasn't until the latter half of the century, with the advent of infrared technology on high-altitude balloons, aircraft, and eventually space-based platforms like the Spitzer Space Telescope, that we could truly see what was happening. By cooling instruments to extremely low temperatures, Spitzer could capture faint heat signals from across the galaxy. Simultaneously, ground-based infrared telescopes in places like the Chilean desert and Hawaii began using advanced cameras to pierce the dust. Teams led by Reinhard Genzel and Andrea Ghez spent years tracking the motion of individual stars near the center. These stars, known as S-stars, were found to be orbiting an invisible point at incredible speeds, with some completing their orbits in just a few years. These high-speed stellar movements provided the ultimate proof that something incredibly massive and compact, a supermassive black hole, was lurking at the heart of our galaxy, finally pulling back the curtain on a truth that had been hidden for all of human history. One particular star, known as S2, travels along an incredibly long and fast orbit that brings it into extreme proximity with Sagittarius A star. Through long-term observation of its trajectory, two independent scientific teams were able to calculate the mass of the object pulling on it. The results were staggering. That object possesses the mass of approximately 4 million suns, yet it is compressed into a region of space smaller than our solar system. Because it does not emit light like a normal star, it is almost certainly a supermassive black hole. None of this would have been possible without the advancements in infrared astronomy. While the thick dust of the galactic bulge continues to block visible light, the narrative becomes clear in the infrared spectrum. We see stars dancing around an invisible power, and where the eye sees nothing, heat glows, revealing the hidden shape of the galactic center. With the right instruments, stellar motion can be measured down to tiny fractions of an arcsecond. When observed over decades, these movements tell an incredible story. In the 1990s, teams led by Reinhard Genzel in Germany and Andrea Ghez in California began using powerful ground-based telescopes equipped with advanced imaging systems to look through the dust. Even in the infrared, the challenges were immense. Earth's atmosphere creates constant turbulence, making stars appear to blur and flicker. To combat this, astronomers utilized adaptive optics technology, where the telescope's mirror adjusts in real time to cancel out atmospheric distortion. Near Sagittarius A star, they found stars moving at breathtaking speeds, whipping around a central point like comets passing a campfire. Some stars reached velocities exceeding 5,000 kilometers per second, fast enough to travel from the Earth to the Moon in just over a minute. The most prominent of these is S2, a bright star on a tight, rapid orbit around a region of total darkness. S2 completes a full revolution in only 16 years. Never before had a star so close to the center been tracked with such precision over such a long duration. Its orbit is an ellipse, just like planets orbiting the Sun, confirming it is responding to a central gravitational pull. From the orbits of S2 and its neighboring stars, astronomers calculated that 4 million solar masses are packed into a volume smaller than our solar system. The only remaining explanation is a black hole, and not just any black hole, but a supermassive one. This provided the most direct evidence to date for the existence of such objects. For decades, black holes were theoretical concepts studied indirectly through X-rays from distant galaxies or computer simulations. Now, for the first time, scientists were watching real stars orbit a truly invisible object in real time. Over the years, the evidence has only grown stronger. More stars have been tracked, some with longer orbits and others even closer than S2. Furthermore, the behavior of these orbits aligns perfectly with the predictions of Albert Einstein's general relativity. These orbits exhibit subtle precessions and shifts in space-time that Newtonian mechanics cannot explain. This means that near Sagittarius A star, gravity is not just strong, it is actively warping the fabric of space and time. In 2002, the GES team published the first full orbit of S2, followed by even more precise measurements from the Genzel team in 2008. Working independently from opposite sides of the globe, their conclusions were identical. A massive invisible object sits at the center of the Milky Way, and its gravity dictates the motion of all nearby stars. When scientists first began to understand black holes, they realized these objects come in various types. While the core concept is simple, a region where gravity is so intense that not even light can escape, their formation and behavior vary greatly. Sagittarius A star belongs to the class of supermassive black holes, but it is part of a broader spectrum. Stellar mass black holes are the smallest, formed when massive stars collapse at the end of their lives. Medium mass black holes are harder to find and may be the missing link between stellar and supermassive types, possibly forming through the merger of multiple stars. Supermassive black holes like our own can reach masses of millions or even billions of suns. Sagittarius A star is actually on the lighter end of this scale. These giants likely grew over billions of years through the steady consumption of gas or by merging with other black holes. Almost every large galaxy seems to harbor such a giant at its core. There is also the possibility of primordial black holes, formed not from stars but from extreme density fluctuations immediately after the Big Bang. Compared to the most violent black holes in the universe, Sagittarius A star is relatively quiet. Many supermassive black holes are highly active, devouring vast amounts of matter and launching brilliant jets across space. Our galactic center is currently in a period of low activity, with only occasional flares in radio, infrared, and X-ray bands. This silence actually makes it an ideal laboratory for study, as we can observe the black hole itself without being overwhelmed by the radiation of a violent feeding event. By comparing Sagittarius A star to other black holes, we can better understand its place in the grand cosmic landscape. The name Sagittarius A star itself has an interesting history. Because we are inside the Milky Way, we cannot see it from above, so we use constellations as landmarks. In the early 1970s, Bruce Balick and Robert Brown used radio imaging to study the central radio source. They identified a compact point at the very core and named the entire complex Sagittarius A. Within this cluster, they found the central engine and named it Sagittarius A star, borrowing the asterisk notation from atomic physics to denote an excited state. The name stuck, even though it is somewhat ironic since the object is the opposite of a star. It emits no light of its own and swallows everything that comes too close. Nearly every galaxy, whether spiral or elliptical, appears to have a massive black hole at its heart. This seems to be a fundamental rule of the universe. The brightest galaxies are powered by supermassive black holes actively feeding on gas and dust. We now believe that these black holes and their host galaxies grow together in a form of coevolution. There is a tight relationship between the mass of a black hole and the mass of its host galaxy's bulge, suggesting they regulate each other's growth. When a black hole feeds, it can blow gas out of the galaxy, slowing down the formation of new stars. Conversely, a galaxy forming many stars can funnel more material toward the center to feed the black hole. By studying Sagittarius A star up close, we can test our theories on black hole growth and galactic evolution, providing insights that explain the structures of the most distant reaches of the cosmos. After decades of research, the mystery of supermassive black holes remains unsolved, yet understanding the sheer scale of the puzzle is progress in itself. If we were to replace the Sun with Sagittarius A star, its event horizon would instantly swallow Mercury, Venus, Earth, and Mars. However, in the grand arena of the universe's largest black holes, Sagittarius A star is far from being the king of the mountain. Consider the black hole at the center of M87, famously imaged by the Event Horizon Telescope in 2019. It possesses approximately 6.5 billion solar masses, making it more than 1,600 times more massive than Sagittarius A star. Its event horizon is large, enough to contain our entire solar system. Even larger is Holm 15A, located at the center of a galaxy cluster over 700 million light-years away, with an estimated mass of 20 billion suns. If we were to swap it with our own central black hole, the gravitational structure of the Milky Way would be completely reshaped, causing stellar orbits to migrate drastically and the central bulge to become far more compact and brilliant. Then there is TUN 618, one of the largest black holes known to science. Compared to it, Sagittarius A star is like a pebble next to a skyscraper. TUN 618 has an estimated mass of 40 billion suns. While light takes about 24 seconds to cross the event horizon of Sagittarius A star, it would take an entire week to cross the event horizon of TUN 618. Interestingly, being more massive does not necessarily make a black hole more dangerous to its distant surroundings. The overwhelming pull of a black hole only becomes apparent when you get close to it. From a great distance, its gravity is no different from any other object of the same mass. If the Sun were magically replaced by a black hole of equal mass, Earth's orbit would not change, the world would simply become dark and cold. The same logic applies on a galactic scale. A massive black hole does not automatically swallow stars every day, the difference lies in its growth rate and level of activity. Sagittarius A star is currently relatively quiet, occasionally consuming small amounts of gas and dust which trigger faint flares in X-ray and radio frequencies. In contrast, TUN 618 is an active quasar, feeding at an incredible rate and forming a brilliant accretion disk that can outshine its entire host galaxy. This gluttony not only makes it visible across the cosmos but also allows it to grow much faster over cosmic time. Scientists believe Sagittarius A star may have been more active in the distant past. Evidence suggests that millions of years ago, it might have been powerful enough to sweep intense radiation across the galaxy, leaving behind remnants like the Fermi bubbles, giant structures of gamma rays extending above and below the galactic plane. When comparing these giants, scientists also focus on their spin. Rotation affects the accretion disk, the formation of jets, and the warping of nearby space-time. While the spin of Sagittarius A star is still being carefully measured, black holes like the one in M87 are thought to spin near the maximum rate allowed by physics. A rapid spin acts like a cosmic blender, whipping up surrounding matter and launching it outward at nearly the speed of light. Sagittarius A star likely began as a smaller black hole and grew slowly by consuming gas, dust, and the occasional unlucky star. In contrast, giants like Tun-6 may have had a head start through the direct collapse of massive gas clouds in the early universe or through frequent mergers in dense environments. Although our Milky Way is unlikely to grow as large as the hosts of those monsters, a future collision with the Andromeda Galaxy will likely give Sagittarius A star a significant growth spurt. Billions of years from now, it could become several times more massive. A black hole does not naturally slow down as it ages. As long as matter falls toward it, it will continue to feed. The difference is simply the availability of fuel. Compared to active galaxies, there is far less gas and dust near the center of the Milky Way. Even when matter does get close, it is often heated and agitated, with much of it being blown back into space by powerful winds before it can ever cross the event horizon. Only a tiny fraction of material actually makes it past the point of no return. By black hole standards, Sagittarius A star is a weak feeder. Its radiation across radio, infrared, and X-ray spectrums is thousands of times fainter than its hungrier counterparts. If our black hole suddenly began feeding at the rate of a quasar, the night sky would be transformed. A brilliant light source would appear at the galactic center, visible even during the day and outshining most stars. While fascinating, its current quietness is likely a blessing for life. A highly active center could emit radiation intense enough to strip the atmospheres of planets even thousands of light years away. Our distance from the center protects us, but the overall habitability of the galaxy may still depend on the temperament of its heart. The future of Sagittarius A star depends on whether it can find new sources of matter. Most stars in its vicinity are in stable orbits and will not fall in. However, over vast time scales, galactic dynamics are unpredictable. A close encounter with a dense gas cloud or the tidal disruption of a star could provide a sudden feast. Recently, astronomers tracked a gas cloud named G2 as it approached the black hole. Many expected a violent eruption, but the event was surprisingly mild. G2 was stretched and distorted, but most of it survived the encounter, proving that not every close approach results in a banquet. Yet, the possibility remains. If a larger cloud or a star were to wander too close, Sagittarius A star could brighten by a factor of thousands. While not dangerous to Earth, the galactic center would become a dominant beacon in the sky. The ultimate awakening will come during the merger with Andromeda. The resulting stir-up of gas and dust will likely trigger a true quasar phase for our central black hole, reshaping the galaxy and regulating star formation for eons to come. For many galactic centers, the black hole is surrounded by a glowing accretion disk where matter spirals inward, heating up to millions of degrees through friction and compression. Yet, we see no such brilliant disk around Sagittarius A star. The reason lies in a delicate environmental balance. Observations suggest that while matter does move inward, most of it is blown away before reaching the event horizon. This is known as a radiatively inefficient accretion flow. The material falling in is not dense or compact enough to radiate efficiently, meaning the energy is carried away in other ways rather than as light. It is like trying to start a fire with wood scattered far apart. The heat is there, but it never coalesces into a bright flame. When the Event Horizon Telescope looked at Sagittarius A star, it resolved a faint, mottled ring of light rather than a smooth, brilliant disk. This confirms the picture of a hot, thin, and chaotic flow of plasma. Even in this state, these faint emissions provide a precious window into how magnetic fields and superheated matter interact under extreme conditions. We live beside a sleeping giant whose hunger is currently suppressed, but the occasional flares of light remind us that the beast is still there, waiting for its next meal. The flares of Sagittarius A star have no fixed timetable and do not correlate strictly with anything we can predict. Because they are hidden behind thick layers of dust, they are deeply mysterious. Whenever a flare is detected, scientists immediately pivot their instruments toward the galactic center, hoping to record as much data as possible before the light fades. The rapid rise and fall of these flares suggest they originate near the event horizon. The timescale of these brightness changes is so short, often just a few minutes, that the source must be incredibly compact, no larger than the distance light can travel in that time. Close to the edge of Sagittarius A star, the rules of the universe seem less like iron laws and more like fluid patterns. Here, gravity is not the only master. Invisible but powerful magnetic fields twist and wind through the plasma like living things. For a long time, these fields were thought to be mere side effects, but we now know they are central to the black hole's strange behavior. These fields are not generated by an internal dynamo like Earth's. Instead, they come from the surrounding plasma. As gas moves, it drags and twists the magnetic lines, tying them into complex knots. Data from the Event Horizon Telescope revealed spiral patterns in the polarized light, proving that the magnetic fields are strong enough to shape the movement of matter rather than just being pushed around by it. In a sense, the magnetic field is in a tug-of-war with gravity. While gravity tries to pull everything in, a tightly wound magnetic field can hold matter back or redirect it. This might explain why Sagittarius A star is so quiet. The magnetic fields may act as a shield, allowing only a tiny trickle of gas to enter the event horizon. The most concise way to describe a black hole is through the Schwarzschild radius, which defines the size of the event horizon. Once you cross this line, you are forever lost to the visible universe. In 1916, Carl Schwarzschild found the first mathematical solution for this kind of object shortly after Einstein proposed general relativity. His equations show that if enough mass is squeezed into a small enough space, gravity becomes absolute at a certain radius. For Sagittarius A star, which has a mass of about 8.54 times 10 to the 36th power kilograms, the Schwarzschild radius is approximately 12 million kilometers. While huge on a human scale, this is surprisingly small in the cosmos, only about 17 times the diameter of the Sun. The event horizon is not a physical surface but a boundary where space and time collapse inward. From the perspective of a distant observer, an object falling in would appear to slow down and fade away, never quite appearing to cross the line due to extreme time dilation. The black center seen in Event Horizon Telescope images is not the black hole itself, but its shadow, a slightly larger silhouette formed because light is bent and swallowed near the horizon. Throughout the mid-20th century, the galactic center remained a mystery. It was the rise of radio astronomy and very long baseline interferometry that finally sharpened our view. By linking telescopes across the globe, scientists created a virtual telescope the size of the Earth, achieving the resolution needed to see the compact heart of the Milky Way. In the 1990s, the advent of adaptive optics allowed teams to track the rapid orbits of stars with unprecedented precision. Space telescopes like Chandra and Spitzer further revealed that the black hole is not entirely asleep, occasionally producing bright X-ray flares. The ultimate breakthrough came in 2022, when the Event Horizon Telescope collaboration published the first image of Sagittarius A star, a blurred but unmistakable ring of light surrounding a dark shadow. This image was the result of years of global collaboration and complex algorithms designed to account for the fact that the matter around the black hole moves at nearly the speed of light, changing the brightness pattern in just minutes. Light does not always travel in straight lines. Space itself can bend and twist it, acting like a giant lens. This phenomenon, known as gravitational lensing, is one of the most remarkable tools in astronomy. For those studying Sagittarius A star, this effect provides a clearer look into the dark heart of the galaxy. Just as a heavy ball placed on a rubber sheet creates a dip that deflects a rolling marble, a massive object like a black hole warps the fabric of space-time and bends the path of passing light. Near the galactic center, where stars and gas are densely packed, a star might briefly pass behind another object, causing its light to be focused and amplified. This is known as microlensing. By studying these distortions, scientists can reconstruct the path of the light and learn more about the structure of the center, even when it is obscured by dust. These gravitational ripples are the few direct clues we have about a region we can never visit, helping us understand the inner workings of the most powerful engines in the universe. Not only can intervening objects lens the light coming from the center, but Sagittarius A itself can bend the light of background stars, even producing multiple images or stretching them into long arcs. Precisely measuring these distortions helps determine the black hole's mass with high accuracy and provides clues about the distribution of matter near the event horizon. Capturing such events is difficult because perfect alignments are rare and short-lived, especially in the highly dynamic central region. A global network of telescopes must monitor this small patch of sky simultaneously to avoid missing subtle changes in brightness or position. These signs were not immediately recognized by early radio astronomers, who occasionally noticed strange increases in background sources but lacked the theoretical consensus or the precision tools to explain them. Today, researchers can not only identify lensing events but also predict them by meticulously tracking the movements of central stars. Even for our most advanced telescopes, the region just outside the event horizon is incredibly tiny on the celestial sphere. Gravitational lensing acts as a natural magnifying glass, boosting resolution, and helping us study the shape of the accretion flow, the distribution of magnetic fields, and the dynamics of orbiting matter. These are all critical details for testing models of black hole behavior. Furthermore, lensing can act as a natural amplifier for faint flares, making them more prominent against the background. In cases of perfect alignment, light from a flare might even travel along two different paths around the black hole to reach us, creating a delayed echo. This effect works across all wavelengths, from radio and infrared to high-energy X-rays, making it a versatile tool for revealing the deepest secrets of this black hole as next-generation instruments come online. Before the light from stars near Sagittarius A star reaches our detectors, it must pass through Earth's atmosphere. While essential for life, the atmosphere is unfriendly to precise astronomical measurements. Pockets of air with varying temperatures cause starlight to bend inconsistently, creating the familiar twinkling effect. For astronomers trying to track the minute movements of stars near a black hole, this twinkling is a major obstacle. For years, even the most powerful ground-based telescopes struggled to produce sharp images of the center. The solution is adaptive optics. Rather than trying to build a better lens, this technology confronts the atmosphere directly. Since the air distorts the starlight, the telescope uses a mirror that can rapidly change its shape to cancel out those distortions in real time. To know how to bend the mirror, astronomers use a bright reference star or a laser to create an artificial star in the upper atmosphere. Computers analyze the distortion of the star hundreds of times per second and send commands to tiny actuators behind the mirror to adjust its surface. When adaptive optics was first applied to Sagittarius A star, it was revolutionary. What once appeared as a blurry blob suddenly snapped into focus, revealing individual stars whose orbits could be tracked year after year. This technology also made spectroscopy more accurate, allowing scientists to decode the velocity and chemical composition of stars in extreme environments. Without adaptive optics, milestones like the measurement of gravitational redshift for the star STWO would have been impossible. In 2019, the world saw the first image of the black hole at the center of Milky 7. Because it has a mass of about 6.5 billion suns, its event horizon is massive, making its shadow easier to image despite its great distance. Its immense mass also means that matter orbits it more slowly, with brightness changes occurring over days or weeks, providing a stable target for imaging. To achieve the necessary resolution, scientists linked radio telescopes across the globe to form the Event Horizon Telescope, a virtual dish the size of the Earth. All stations had to observe simultaneously, with their data synchronized by atomic clocks. The amount of data collected was so vast it had to be physically shipped on hard drives to central processing facilities. In April 2017, the weather was ideal across all sites, allowing for a successful observation at a wavelength of 1.3 millimeters. After years of complex data processing and algorithm development to fill in the gaps of the virtual telescope, the famous orange ring was revealed. This image proved that we could directly image a black hole and paved the way for the much more difficult task of imaging Sagittarius A star. Sagittarius A star is smaller, meaning its shadow appears tiny on the sky, roughly the same angular size as a donut on the surface of the Moon as seen from Earth. More importantly, it is much more active. While M87 changes over days, Sagittarius A changes over minutes. Matter orbiting near its event horizon completes a circuit in a very short time. This means that while you are still integrating data, the target itself has changed its appearance. Imaging it is like trying to take a long exposure photograph of a puppy chasing its tail in the wind. The result is naturally blurred. Furthermore, because we are looking through the disk of our own galaxy, the radio waves from Sagittarius A star are scattered by interstellar dust and ionized gas. Correcting for this scattering requires intense processing that inevitably loses some detail. To produce the 2022 image, the team had to generate thousands of possible images and look for features that remained stable across all versions. The result was a victory of technical innovation over incredible physical hurdles, proving the existence of the giant at the heart of our own galaxy. In the public eye, these images are once-in-a-decade achievements, but for science, they are just the beginning. One of the biggest unknowns is the black hole's spin. Spin determines the shape of the event horizon, the orbits of nearby matter, and the energy of any potential jets. Because Sagittarius A star changes so quickly and the final image is a time average, the clues about its spin are somewhat blurred. We also don't know the exact orientation of its spin axis since it lacks the prominent jets that act as pointers in other systems. Future observations focusing on polarized light will help map the magnetic fields, while faster snapshots might eventually reveal hotspots racing around the horizon. Every bit of new data helps tighten the constraints on general relativity and rule out alternative theories. The interior of a black hole is not an area we can explore, it is a box that can never be opened. In classical physics, once you cross the event horizon, all paths lead to the singularity, a point of infinite density where the laws of physics break down. However, modern physics asks if the singularity is real. At the scale of quantum gravity, perhaps the singularity is replaced by a structure of finite density. Some models even suggest that the interior could be connected to other regions of space-time through wormholes. Others propose that black holes might be fuzzballs of strings or that information is preserved on their surfaces in ways we don't yet understand. While the event horizon prevents us from seeing inside, the mathematical models we build to describe these interiors force us to test the very limits of our understanding of time, space, and causality. Despite the mountain of evidence that Sagittarius A star is a supermassive black hole, science requires us to keep testing our assumptions. Could it be something else? Some suggest it might be a dense concentration of dark matter, but dark matter typically doesn't clump tightly enough to fit 4 million solar masses into such a small volume. Others propose boson stars, theoretical quantum condensates that are incredibly compact but lack an event horizon. There is also the idea of gravastas, where a shell of exotic matter surrounds a core of dark energy. While these objects might look like black holes from a distance, they would lack a true point of no return. So far, all our observations, the orbits of the S stars, the nature of the flares, and the shadow imaged by the Event Horizon Telescope point toward the black hole as the most likely and consistent explanation for the dark giant at the center of the Milky Way. More exotic possibilities for the central object include concepts like fuzzballs from string theory or even stable wormholes. The common challenge for these alternative theories is that every measurable external phenomenon we have observed so far aligns more closely with the properties of a black hole. However, maintaining an open mind is the primary driver of scientific progress. Every sharper observation serves as a new interrogation of our current understanding. The galactic center is vastly different from the quiet suburban region where our Sun resides. Near Sagittarius A star, stars move at incredible speeds, with some completing their orbits in just a few years. In the chaotic youth of our galaxy, the central black hole likely acted as a gravitational anchor, pulling in matter and accelerating the formation of the dense galactic bulge. Simulations suggest that a central black hole can stir up gas, sometimes funneling it inward to feed itself and build the bulge, and at other times, when active, blowing gas away to suppress the formation of new stars. The balance of this influence depends on the black hole's growth rate and energy release. The close relationship between the mass of the black hole and the mass of the galactic bulge suggests that they evolved together. If Sagittarius A star had a major impact on the Milky Way, it likely occurred during its more active phases when its powerful winds and jets could clear out gas, shaping the evolution of the spiral arms and the central bar over billions of years. The Fermi bubbles remind us that its influence can extend far beyond the galactic plane. While the black hole's direct gravitational reach is relatively short, the Sun and the outer spiral arms are mostly shaped by density waves, and the disk's own gravity. Sagittarius A star remains both a driver and a passenger in the story of our galaxy, sometimes watching from the sidelines and at other times stepping on the gas. Engineers, astronomers, and computational scientists are now building the next generation array that will make the current Event Horizon Telescope look like a prototype. The images of Sagittarius A star we see today were created using technology from several years ago. In the field of astronomy, there is always a delay between data collection and publication. By the time the results are released, the tools have already been upgraded. The biggest leap will come from adding more stations around the globe. More sites mean denser sampling and sharper images. While geographic, financial, and political constraints currently leave gaps in the virtual array, expanding to sites in Africa, the Pacific Islands, or even floating platforms at sea could significantly improve our view. Even bolder plans involve moving telescopes into space. A space-based array working with ground stations would create a virtual telescope larger than the diameter of the Earth, dramatically increasing resolution. This could allow us to create movies of Sagittarius A's evolution in real time. Data links will also be upgraded, moving from physical hard drive shipments to ultra-high-speed links that allow for near instantaneous processing. In terms of algorithms, machine learning will be increasingly used to identify robust patterns in the data, improving clarity, and automatically flagging transient events. We will also expand from observing at a single wavelength to multi-wavelength studies, capturing the black hole in its true physical colors. Longer continuous observations and smarter weather scheduling will increase our chances of catching hotspots racing around the event horizon. Larger projects like the Square Kilometer Array, while not designed for the same resolution as the Event Horizon Telescope will help us see even fainter details and weak outflows. Future visions even include lunar stations, where the lack of an atmosphere would allow for constant, crystal clear coordination with Earth-based telescopes. The spin of Sagittarius A star can tell us the story of its birth, whether it grew slowly over eons or through several violent feeding sessions and mergers. However, spin cannot be seen directly, it must be inferred from the behavior of light and matter near the event horizon. One of the most promising keys is X-ray polarimetry. Polarization is the orderly direction in which light waves vibrate, and magnetic fields and the surrounding geometry leave unique fingerprints on this light. Near Sagittarius A star, falling matter is heated and produces X-rays. If the black hole is spinning, it warps the surrounding space-time, changing the path and polarization of these X-rays. By measuring these properties with high precision, we can reverse engineer the geometry of the accretion flow and the strength of the spin. Until recently, X-ray polarimetry was only a dream, as it requires incredibly sensitive instruments on satellites like NASA's Imaging X-ray Polarimetry Explorer. Future missions with larger apertures and faster timing will allow us to track the swing of polarization angles in real time during flares. This will not only reveal the spin but also tell us how the spin axis is aligned with the rest of the galaxy. Even if Sagittarius A star appears quiet today, its spin may be a hidden engine, silently influencing the dynamics of the surrounding gas. That concludes our discussion for today. I hope this journey to the heart of our galaxy brings you wonderful dreams and a beautiful day ahead. We look forward to seeing you in the next episode.